So I just finished doing the Hess law video and realized, hang on, because we know bond enthalpies, we know how to work out the enthalpy of anything without actually ever having to do a reaction. So I forgot about bond enthalpies, which is a bit silly of me. All right, so this is probably the best use of Hess's law. So what we've done is, because we've got so many different types of reactions that we've got enthalpies for, what we've done is we can work out what the enthalpy of every different type of bond is. Now, it's slightly different for different reactions. It's basically an average. So average bond enthalpy is the amount of energy required to break 1 mole of bonds in the gaseous state averaged across a range of compounds containing that bond. And so it won't be 100% accurate, but it's not too bad. Okay, so we know what the bond enthalpies for everything is. So basically you can add this all up like Lego and work out what the bond enthalpy for anything is. So that's what we're going to do. So first of all, just going to look at the bond length and bond polarity and bond enthalpy and the relationship between that. And so these compounds here are the ones we're going to focus on, because these are very electronegative at the top. There's a high concentration of PosNeg. You think they might be exposed to attack, electrophilic or nucleophilic attack. But actually their bond enthalpy is really, really strong when they're really, really polar. Their bond length is really tiny. As you can see, it's getting really, really tiny, and the bond strength is getting really, really large. And basically they're sticking together very, very well. So the electronegativity difference is here. And if you don't need to do this one, but En divided by 3.2 times 100 gives you the ionic character. And so you can see that there is a lot of ionic sort of strength to this very polar bond. And so that's another indication of how strong the bonds are. So small bond length, high polarity, high bond enthalpy is what they want you to be aware of. And we've visited that already with bonding, and we'll come back to it it'll determine certain reactions as well with organics. Okay, so let's back to this again. So the Hess's law, so sometimes enthalpy is reactants minus products. Sometimes it's products minus reactants, all depending on what is the type of enthalpy you're using. Now, so far we talked about just enthalpy, innate enthalpy, and we did, products minus reactants. And that was just innate enthalpy. And then I think we talked about reaction enthalpy, or maybe we haven't. But now we are definitely going into specific types of enthalpy, and that's extremely important to know whether it's reactants minus products or products minus reactants. And so the bond enthalpy, the definition we just gave, was the chemical, the thing, breaking off into a gaseous atom, breaking up into gaseous atoms. And so if we look back here, these things are when this breaks up and turns into hydrogen gas, basically. And so because that's the case, then to get from A to B, it's okay to add this one, but this one we can't add it, we must reverse it. So it's reactants minus products, not products minus reactants. Now the next one we'll do is formation, if I jump the gun a little bit, and that's gaseous atoms to the chemicals. So it'll be this one. So it'll be the reverse. It'll be products minus reactants due to Hess's law. Okay, so Hess's law not only teaches us how to work out the equation, whether it's reactants minus products or products minus reactants, but actually lets us do the thing as well. Okay, so here is just one example, because now you can see how complex it is. It's extremely powerful, but it's also complex because you've got to know what all the bonds are, and you're not going to know what all the bonds are unless you draw the correct Lewis structures, because there are 3 NH bonds, and this is not an NN bond, it's actually an N triple bond. And so first thing you do is draw out the Lewis structures. The second thing you do is clearly write out bonds broken, bonds formed, and the total change. So you want to do this clearly. So number 1, you don't get it wrong. Number 2, you get marks when you make a mistake. So the bonds broken, there's a triple bond. If you look up your data booklet, that's going to give you this value. And there's 3 of the HH bonds here. There's 3 of those. So you've got to be really, really careful. All right. So that adds up to this amount of energy breaking the bonds. Now, forming the bonds, there's 3 of these NH bonds, but there's 2 times 2. So there's actually 6 in the NH bond. So it's 6 times this. So this is the bonds formed. Okay. Getting pretty tricky, I can see. So just double check your formula, reactants minus products. So make sure that's written out correctly. So formula, then substitute, and then units. Okay, absolute bare minimum is what I've written here as a model of how to set it out. Do not dare write less than this. It's okay to write more, but do not write less. Otherwise, you'll, number 1, get it wrong. Number 2, not get error carried forward and marks for if you do make a mistake. Okay, so if you add those 2 together, the answer is minus 90 kilojoules per mole. And this, obviously, we can do absolutely anything you could possibly think of, even reactions that don't exist. We could work out what the enthalpy for them is, and one day someone might work out how to make them exist. Okay, and then we'll already know the enthalpy. Okay, pretty clever, yeah? Make sure you do quite a few of these examples. It's good practice for quite a few different skills, including Lewis, Hess, and enthalpies.